In section 6.4, we're going to look at one result, and that is the second part of the fundamental theorem of calculus, sometimes called FTC Part 2. So again, we're going to look at this one result, understand what it's trying to say, use it in an example problem. This is going to be a fairly quick section. So the second fundamental theorem of calculus, or FTC Part 2, says that if f is a continuous function on an interval and a is a number in that interval, then the function f of x, capital F of x, defined by capital F of x equals the integral from a to x of f of t dt, that is an antiderivative of f of x. Now, I want to make clear that this theorem is very, very complicated for one reason, and that is notation. It's very hard to parse through what's actually being said here. When you really get into it, it's not saying much. We're going to try to understand what it's really saying in just a bit here. But there is lowercase f of x, lowercase f of t, capital F of x, an integral with an x in the bounds, and there's just a lot to kind of get through in that. All right, so we're going to spend some time talking about why that's important. All right, so why is this important? Why is this theorem useful? Why is this a fundamental theorem of calculus? And the point is that this guarantees the existence of an antiderivative even if we cannot find one algebraically. And why is that a useful thing? We talked about existence theorems in chapter 4 a little bit. Why is an existence theorem important? And it's the same idea that, if you were told that there's buried treasure somewhere, would you get off your butt and start looking for that buried treasure? And the answer is probably no, because there's no guarantee that it actually exists. But if you were given that guarantee, it might be worth looking for. We're going to be looking for antiderivatives. We're going to be using antiderivatives. But if we don't even know an antiderivative exists, then it's not really worth, searching sometimes. So this theorem guarantees the existence of an antiderivative and tells us a way that we can represent it as well. But that doesn't mean we can find some algebraically. So here's the motivation. Consider the area under e to the negative x squared from 1 to negative 2. Or negative 1 to 2, I should say. E to the negative x squared is a pretty simple looking function. It looks something like this. This is actually the shape of a bell curve, if you know what that is, or at least it's that function kind of translated a little bit. But we're looking for the area from negative 1 to 2, this area. And we should be able to find that. That's a very simple kind of picture to draw. We should be able to estimate what that area is, and we can make sense of this being equal to the integral negative 1 to 2 of e to the negative x squared dx. The problem here is that there is no nice way of writing the integral of e to the negative x squared, of writing an antiderivative of e to the negative x squared. There's no nice way with the tools that we have so far. There's really just no nice way of doing it. There's some ways around it using series, and you're going to talk about that in Calc 2, but really there's no nice function you can write that whose derivative is e to the negative x squared. But there's still an antiderivative of this function. It exists. There's just not a nice way of writing it down. So what we have here is that the function capital F of x, which is going to be the integral from let's actually do the integral from negative 1 to x of e to the negative t squared dt This is an antiderivative of e to the negative x squared. Note that the t here is a dummy variable. You could use any variable you want there. It doesn't really mean anything. We just need something different than x in there. You could use anything you want. That's there. And let's talk about what this means, this negative 1 to x. This is a function of x. We plug in x's function. That means we plug it into the top bound. And let's say we plugged in f of 2. That would give us, actually, let's do f of 1 would give us the integral from negative 1 to 1 of e to the negative t squared dt, something that we don't really know how to find at the moment. And that would be the area under the curve from negative 1 to 1. Capital F of 2 would give us the answer to what we're trying to find, the area under here. Okay, we're now going to move into doing a practice problem to kind of see what this is all about. But again, we're not saying much here. We're saying that this theorem guarantees the existence of an antiderivative. And that's very important, but it's not really much that we're saying past that. Now let's move into a practice problem to kind of parse through the notation, try to understand what's going on. All right, so we have this expression here. We want to find the derivative of this function, 1 to the x, integral of 1 to the x, 1 plus t to the 200 dt. And I'm not going to use the fundamental theorem of calculus part 2 at this point. So this means that I need to find an antiderivative of 1 plus t to the 200. And note that that's going to be 1 plus t to the 201 over 201. It's like the reverse power rule. Having the 1 plus t there makes it a little bit different, but you can verify that's true with some with the derivative rule and the chain rule. So this integral we can write as this function 1 plus t to the 201 over 201 evaluated from 1 to x is going to be, we have the derivative here, plug in the top bound, that's 1 plus x to the 201 over 201, minus 1 plus 1 to the 201 over 201. And now I need to find the derivative of those things. So the derivative of 1 plus x to the 201 over 201 is going to be 1 over 201 times 201 times 1 plus x to the 200 using the chain rule, and the derivative of a constant is 0. So this just becomes 1 plus x to the 200. And that is the derivative of 1 over x to the 1 plus t to the 200, because we said that this 1 over x to the 1 plus t to the 200 is an antiderivative of 1 plus x to the 200. So another way to think about the fundamental theorem of calculus is saying that if we take the derivative of the integral of something, they kind of cancel each other out. We have to be a little bit more careful than that, but that's basically what's going on. The derivative of the antiderivative just cancels each other out. Let's now use the fundamental theorem of calculus part 2 just to do this very quickly. And we kind of already said it, right? We have we can say that this is equal to the derivative of capital F of x. Capital F of x is an antiderivative of 1 plus x to the 200. So if you take the derivative of the antiderivative, you should just get the original function back, 1 plus x to the 200. We can do that very quickly with the second part of the fundamental theorem of calculus. All right, in conclusion, this theorem is weird. It doesn't tell us a whole lot, and there's a lot of notation to parse through. Doing examples like this can help you get more familiar with what's going on. You can kind of see that the derivative and the antiderivative are canceling each other out. And we'll do some more practice problems in the next video.